Hello, my name is Joe Bierer and I'm with Bierer Associates, and today we're going to talk about our ST800. The part number ST800 stands for Service Tester 800 amps. This unique tool to the utility industry does two things simultaneously. First, it will test the integrity of secondary conductors, and it will also identify secondary conductors, and there are a couple applications for identifying primary conductors. Let's begin by noticing how small, lightweight, and compact the ST800 is. It's also equipped with a magnetic back that will attach to ferrous material. If the surface you're working on is not ferrous, the unit can be easily handheld while in operation. Depending on the data manufacturer, there are either two switches or two push buttons located on the front of the device. The one on the right is your on-off switch or push button, and the one on the left is your V or I for voltage or current. There is also a green test light, and this light comes on whenever the unit is in operation or attached to a live circuit. The green light will blink as the unit pulses. The ST800 is available with two different size clamps for connection. The small connectors, as seen here, work better for small meter bases or areas with limited space. We also have available, upon request, a larger, more durable insulated clamp. So let's begin our first demonstration by connecting the clamps to this meter base and turning the device on. Once all of our connections have now been made, you will notice that the black conductor is connected to the neutral and the red conductor is connected to one of our hots in the meter base. We should now turn the device on in the V position. The V position will verify and make sure that neither the neutral nor one of the hots that we have it connected to is open, as demonstrated here by reading 120 volts. Also notice here that the ST800 count is already at 4. In the V or voltage position, the ST800 will alternate between a voltage reading and a count reading. If we flip the V and I button or V and I switch to the current or I position, it will alternate between the same count reading and a current reading. The maximum count is 158 counts, and I will explain later in the video how the count number can become important troubleshooting information. As I zoom the camera in here, let's focus our attention on something very important. As the ST800 gradually increases in count, we want to focus our attention on how much current it increases per count. This information is very important for a couple different reasons. One, if the ST800 current increases approximately 8 amps or greater per count, then we know the conductors that the leads are attached to are able to source a high amount of current, and more than likely the ST800 will achieve 800 amps fairly easy. This is obviously a good service that we're attached to in this demonstration, and at approximately 50 counts we're already up close to 700 amps. Now let's let the ST800 continue up to 800 amps and talk about how high the count number is and what that means. We'll notice it stopped at 52 counts at 800 amps. So the first thing we noticed on this service was that the ST800 was able to achieve a much greater than an 8 amp per count increase. The other thing we noticed is the count number itself, stopping at 52. Since we were quickly able to determine that both the neutral and the hot on this service are good conductors, now using the count number 52, we're able to compare that with the other hot and the same neutral connection. But first, cycle the ST800 power off. By simply moving the red lead over to the other hot and then turning the ST800 on again and performing the exact same test, we should see an equivalent or close to 52 counts at 800 amps. This would verify that all three conductors are now good and this service is then good as well. It is important to remember that some services may not be able to achieve 800 amps. There are a couple reasons the cause is. The conductor size may be too small, such as number 4 wire, or the service may have a long distance causing high voltage drop. Or it could be a combination of both small cable and a long service distance. Whichever the case may be, you're looking for consistency between all three connections. As an example, if our first test between the neutral conductor and one of the hot conductors was only able to achieve 600 amps, then we would expect to see 600 amps between the same neutral connection and the other hot conductor as well. If the neutral is the same size conductor as both hot conductors, the connections between both hots would also expect to see 600 amps. If the hot conductors are larger than the neutral, then you should expect to see a higher current reading between both hot conductors. In the same meter base, I've moved the black lead over to the other hot conductor to better demonstrate how the STRCV can identify each conductor. With the ST800 pulsing 800 amps, we want to take our STRCV and put it in the high position. This is for 300 amps and greater. The medium switch position will be used for anything between 350 amps, and the low switch position will be used for anything less than 50 amps. Notice when we put the STRCV on the red conductor, every time the ST800 pulses, the arrow points up, and every time the ST800 pulses, the arrow points down on the black conductor. This means that every time the ST800 pulses, it goes back towards the ST800 on the black lead and away from the ST800 on the red lead. We will now identify the two conductors we are attached to in the meter base at the transformer. With the ST800 still pulsing 800 amps and the STRCV still in a high switch position, we want to afford ourselves the most room possible. To get the most reliable, consistent reading, place the concave STRCV cone tip perpendicular to the conductor, and also as far away as possible from the other conductors. Notice the lit LED and the corresponding arrow. The arrow is pointing up into the transformer and away from the ST800. If you recall from our earlier example, this is the same conductor that we were attached to with the red lead. So not only have we identified a conductor that the ST800 is attached to, but we have identified which lead the red conductor of the ST800 is attached to, which just so happens to be the hot conductor. We can verify our connection by testing the other hot conductors, that there is no pulse on those as well, but only the conductor we're attached to with the ST800. We also want to be able to identify the neutral conductor, and we will perform this in the same manner as we did when we identified the hot conductor. Since the black lead of the ST800 is attached to the neutral, we're looking for a pulse in the opposite direction as the hot, so the pulse should be pointing down. Here is the hot conductor pointing up, and once we find the neutral, it's pointing down in the opposite direction as the hot pointing up. So now we've been able to identify both conductors. If the situation ever occurred where you're unsure where the service is fed from, a preliminary check at the bushings can be made to verify the source of power for the service. Again, notice the direction of the arrow and the indicating LED. With the arrow pointing to the left, this indicates that the neutral is still connected to the black lead of the ST800, since the pulse is going back to the ST800. With the arrow pointing to the right or into the transformer, this indicates that it's still connected to the red lead of the ST800 since the pulse is going away from the ST800. Now we want to demonstrate how to use the ST800 to identify the primary source cable in a single-phase pad mount if the feed in and feed out are not labeled, or to verify labeling. While performing this test, always connect the red lead and the black lead to the hot bushings of the transformer. When performing this function of the ST800, it is important to remember which lead you have connected to the X1 bushing and the X3 bushing, as I'll show later in the video. In the V position or voltage position, the ST800 should read 240 volts. By connecting the black lead and the red lead to both hot bushings of the pad mount, we maximize the turns ratio of the transformer. This means that once the ST800 achieves 800 amps on the secondary side, it will maximize the available current to identify on the primary side of the transformer. Remember, on the secondary side of the pad mount, the current is high at 800 amps and the voltage is low at 240 volts. The opposite is true on the primary side, whereas the voltage is high but the current is low. So it's very important to remember to put the STRCV in the low current switch position when identifying primary cable. With the ST800 now put in the I or current position, we're going to allow it to ramp up to 800 amps before we attempt to verify or identify which primary cable is the source cable feeding this pad mount. Now that the ST800 is pulsing 800 amps, we will attempt to identify which primary cable is the source. As you may have already noticed in our video, the H1B bushing has an arrestor attached to it, so it is obvious which primary cable is feeding this pad mount. But for demonstration purposes, the result would be the same if another single-phase pad mount were in series with this one. Again, with the red lead and the black lead both connected to the hot secondary bushings of the pad mount, we should get an indication only on the primary cable feeding this pad mount. Notice how the LED in relation to the arrow pointing up is on. If you recall, we have the black lead from the ST800 attached to the X1 bushing. Therefore, whenever we check the primary side, the arrow is going to be pointing up back into the transformer. Or if you recall, anytime you check the black lead pulse, it always goes back towards the ST800. If we were to reverse this and put the red lead from the ST800 on the X1 bushing, the opposite would be true. The light pointing down would be lit on the STRCV. If we were to have a primary cable located on the H1B bushing, there would be no pulse at all, since this would be considered downstream. Remember, the pulse can only go back towards the source, or what we can consider upstream, such as it is indicated here by the STRCV. Also notice where the STRCV probe tip is located. It must be located above the concentric, rest firmly on the primary cable in the concave perpendicular to the primary cable. If this was the last primary pad mount in series with other pad mount transformers, what you would notice in every succeeding pad mount transformer going back to the riser pole is the same light sequence on the STRCV. In other words, every H1A primary bushing cable would have a light pointing up going back to the ST800, and every H1B primary bushing cable would have the light pointing down. This would indicate which primary is feeding the pad mount and which primary is feeding out of the pad mount. Remember, it's not important which color clamp you have connected to the X1 or X3 bushings. It's only important to know which one it is. That way you can identify it on the primary side. Now we will demonstrate how to use the ST800 to identify primary energized or de-energized cable in a manhole or a ditch. Our first demonstration will be to use the ST800 on de-energized isolated primary cable with a secondary power source available. Notice how we have the ST800 black lead attached to the secondary power source and the red lead attached to the concentric of the de-energized isolated cable we want to identify. Again, it does not matter which lead you attach to the hot, secondary power, or the concentric, but best be aware of which one it is so you can identify it in the field in the manhole or the ditch. As you can see from our demonstration, by attaching the red lead to the concentric, we will now be looking for the arrow pointing away from the ST800 in the manhole or the ditch. Once we've made our proper connections, go ahead and turn on the ST800 and take note of the voltage. Make sure that we have 120 volts and the unit is operating properly. Allow the unit enough time to ramp up and achieve 800 amps before we begin our testing. While conducting this test, since one of our leads is actually connected to the concentric of one of the primary cables, there are many paths to ground, so it is important to put the STRCV in the low current setting. This will allow the STRCV enough sensitivity to pick up the primary cable in a manhole or a ditch. Before leaving the near end to identify the de-energized primary cable in a manhole or a ditch, verify correct operation. Notice by testing the concentric above where the red lead is attached, we have an arrow pointing up or away from the ST800. If we were attached the black lead at this location, the arrow would be pointing down or back towards the ST800. And by testing on the opposite side of our red clamp, we should get an opposite arrow, so it's pointing down towards the ground. Now that we've verified that the STRCV is working properly at the near end, we can go out to the location to identify the de-energized primary cable. By looping all the primary cable up in this dog box, it replicates a manhole or a ditch. With the STV still in the low current setting, check each cable and verify which cable has the pulse on it. As you can see, the orange cable has the pulse and is our de-energized primary cable. We can also go to the endpoint of the de-energized isolated primary cable and verify the concentric pulse there as well. Our next demonstration is to identify energized primary cable. Notice our connections are the same as when we identified de-energized primary cable, with the black lead connected to the secondary power and our red lead connected to the concentric of the energized primary cable we want to identify in a manhole or a ditch. Notice this cable is not de-energized and is in fact energized to 13,800 volts. Once our connections have been made, verify that the ST800 has 120 volts of secondary power available when the unit is turned on. Also allow the unit enough time to achieve 800 amps before we begin identification. Once the ST800 has achieved 800 amps, on the near end, verify the correct pulse direction above and below the red lead. Once we've verified that the STRCV is working correctly on the near end, go to the location to identify the primary cable in the field. Make sure the STRCV again is in the low current setting and begin testing each primary cable for the correct directional pulse. As you may have noticed from the first set of tests we just conducted with the STRCV in the low current setting, we received no signal either direction. This may be possible since the red lead is connected to the concentric. There may be too many multiple paths to ground on the near end. In a situation such as this, we actually recommend connecting our CT clamp adapter to the STRCV so the current pulse pickup is much more sensitive. When using the CT clamp, take note of the red arrow located on the side of the unit. The red arrow must be pointing away from the ST800 or the sender and towards the ground or your concentric on the far end. Insert the CT clamp plug into the receptacle located at the bottom of the STRCV and clamp it around the primary cable to be identified. Notice your directional arrow pulse on the STRCV. Again, since we have the red lead attached to the concentric on the near end, the pulse arrow is pointing away from the ST800 towards the concentric on the far end. Clamp the CT around the remaining primary cables and verify that there is no pulse on them. Just as we did when we verified de-energized primary cable, we can now take the STRCV to the far end and verify the concentric on the energized primary cable. Our directional arrow should be pointing towards the ground and away from the ST800. This concludes our ST800 training. If you should have any questions or concerns about any of the demonstrations that you've seen in this video, you can give us a call at 803-786-4839 or email us at customer_service@BiereRmeters.com. Thank you and have a great day.